Hi everyone, it's Mr. Youngren again. Welcome to our final lesson of Unit 3. We're going to be looking at our last set of tables and writing equations. That's going to be with exponentials. So in this lesson, we're going to be working on standards 6.4 and 7.4, being able to write equations of exponential functions from the table of values, and also writing exponential functions given information from various contexts. So like always, we have an opener to start out with. I know it says linear or absolute value, but now that we have one quadratic, be on the lookout that one of them might be quadratic. So go ahead and hit pause, work through that opener, and then I'll meet you back here for a quick discussion on the opener, and we'll go through the lesson. All right, welcome back. Hopefully, at the very least, we're able to find those changes in y's and changes in x's. In both cases, at first glance, it looks like we do not have a constant rate of change, but remember what we always need to check, and that is what happens if we take a change in y and divide it by a change in x. So in table A, no matter which change in y we divide by its corresponding change in x, we're always getting some form of -1/2. So telling us that this actually is constant, even though at first glance it does not appear that way. So we need to check change in y divided by change in x. So since it is constant, and we never switch from subtracting to adding, this is linear. So our slope, being any of the change in y's divided by change in x's, is -1/2. And remember, we can pick any point from the table to represent our equation. I went ahead and chose 2, 2, where the x-coordinate, the sign was switched, the y-coordinate, the sign stays the same. Now on B, again, at quick first glance, I'm seeing all different changes in y's. So I'm thinking maybe non-constant. However, I know I need to check what is change in y divided by change in x. So when I went ahead and did this, for every change in y divided by change in x, I'm getting either +3 or -3 as we get towards the end of the table. So this is telling us that it is constant with the turning point. So this is absolute value. Now, I didn't write the equation in yet because remember we want to decide, does this absolute value open up or does it open down? We're going to do that by making a quick graph. So our turning point, at least as far as we know, is wherever we switch from adding to subtracting, which is right there. So if I go ahead and plot 1, 3, to get to these next points, if I want to go to 3, -3, I'm going to go right and then down, or even 0, 0, right? It's left and down. So no matter what, this is opening down, telling us that our slope or our a value needs to be negative. So it's -3, followed by the turning point of x -1, switching the sign when I place it in the equation, and then +3. All right, so again, continue to work on building those habits and remembering to always check change in y divided by change in x. Right, now our last function with exponentials, know that there's a couple giveaways with exponentials. So let's actually first, so let's talk about that actually. How can you tell if a table is exponential? There's a few different ways. Okay, so first one is that it is non-constant. When we say non-constant, it's non-constant in the change in y's. Okay, but we can also see the asymptote. So we should be able to see a bunch of decimals approaching a certain number. So look for the y values So this is usually a clear giveaway. If I look at this table here, I'm seeing all of these numbers, -3.5, -3.7, -3.875, right? All these ugly decimals, you're getting really close to -4. This is what is telling you, or at least giving us an idea that this is in fact exponential. But what I want to see is, do we also see the non-constant in change in y's? And is there a pattern of multiplication or division? Right, and that's going to be within the change in y. It's kind of like what we did with quadratics and finding the second difference. So let's go ahead and find all of these changes in x's and changes in y's. Change in x, we're just adding 1. And in the change in y's, I'm going to really just focus on the ones that give me a clear value, right? So like -3.875 and -3.75, we are adding a weird amount. Now that weird amount doesn't even matter. If you've got a calculator, go ahead and use it. But we're going to see if we even need that value. Okay, let's go ahead and check. So from negative 3.75 to negative 3.5, that one's a little bit easier. I can see I'm just adding a quarter. Negative 3.5 to negative 3, I'm adding a half. And now we can see I'm adding 1 and then adding 2. So much clearer idea. Right? I don't necessarily need that decimal value, at least not yet. So I'm like, okay, these change in y's are all different, but make sure that we're looking for change in y divided by change in x. And clearly, right from the first set of values, we're getting different amounts for our rate of change, right? 0.25 divided by 1 is very different than 0.5 divided by 1, or 1 divided by 1, or 2 divided by 1. So definitely non-constant. So now, do we see a pattern in these change in y's thinking about multiplication or division? So if I take one change in y to get to the next, I know that I can't add the same amount, right? If I was looking for a second difference, I would have to add 0.25, then add 0.5. So that second difference is non-constant. This is where I now resort to, can we multiply or divide? Well, I know if I've got 0.25 to get to 0.5, I can multiply by 2. I've got a half to get to 1, multiply by 2 again, and 1 to 2, multiply by 2 again. So we now have everything on our table that we need. So the multiplier is whatever we're doing in the change in y's, and that is that we're multiplying by 2. So since we're multiplying by 2, that tells us that this is going uphill. It's an increasing function. The bottom 4, we want to look at those decimals, what we talked about at the beginning. And what are they approaching? They are approaching -4. Now, we want to be very careful here, right? A lot of students might say, you know, it's actually approaching -3. Well, if we look at this, I've got -3 already in my table. So remember, the bottom 4 is a value that we get really close to, but it should never actually show up. So -3 is not even an option because we have it in our table, right? And if we look up, all those values are actually getting much closer to -4, which is our bottom 4. Now we got to do is piece this together. So y equals 2 to the power of x minus 4. So only a couple things that we need here. All right, let's go ahead and turn this over and work on the next problem. Starting with our normal set of habits in finding changes in x's and changes in y's. Even though all the change in x's are adding 1, I'm still going to write that down because we want to pretend as if we have no idea that this is exponential. Now my changes in y's, subtract 18, and subtract 6, and subtract 2, then subtract 0.67-ish, and then the rest, right, it's like minus 0.22, and then a weird amount towards the end. And so we don't even care about that difference there. Let's just focus on these ones that are nice numbers. So again, in these changes in y's, are they constant? No, right? -18 divided by 1 is -18. -6 divided by 1 is -6. So definitely not constant. If we went ahead and looked for our second difference, I would have to add 12 and then add 4. So that's not constant, right? So see how we can rule out all of the other functions pretty quickly. And now we can pretty much say with confidence that this is exponential. Now to confirm that, we'll see, can we multiply or divide these changes in y's to get the next? Well, 18 to get to 6, I'm having to divide by 3. 6 to get to 2, divide by 3 again. 2 to get 0.67, divide by 3 again. So our multiplier, we're dividing by 3. Now, when we divide by 3, we actually are doing, or we are actually multiplying by 1/3. Okay, dividing by 3 and multiplying by 1/3 are the exact same thing. So we want to make sure that we are using this 1/3 in our equation, right? That's what usually if we see a downhill or a graph that's decreasing, it's because of that multiplier being a value less than 1, or even more specific, between 0 and 1. So we don't, even though we're dividing by 3, we're going to use times 1/3 as our multiplier, right? They mean the exact same thing. So our bottom 4, again, what are these numbers getting close to? A little bit easier here, but we can see that's getting smaller and smaller, or smaller and smaller, and closer to 2. And that is our bottom 4. So our equation is y equals 1/3 to the power of x, and then plus 2. Right, so decreasing because of the 1/3, and 2, right, we're getting closer and closer to 2. Right, you have a couple problems for your group practice. You're going to actually save those for in class, and we're going to go ahead and jump to the next page. So where I want to pick off is you're going to skip group practice problem number 3 and group practice problem number 4. And we're going to go ahead and talk about some of these exponential equations because there is a little that we're going to add on to. We've actually seen this in our second lesson. So we'll do one of these and then we're going to actually flip this page over. So when we're writing equations giving a bunch of different information with an application, our equation is slightly different. Okay, and this is because we're going to assume the bottom floor is 0. So it's really like plus 0 for that bottom floor. But it's that A value that we're really focused on. So the A value is just the starting amount. So what we're going to do is see if we can identify that starting amount. B is still the multiplier. And we're going to see if we can't build an equation and then use that equation to go ahead and make predictions. So it is estimated that there are 25,000 polar bears left in the world. I'm going to circle that or underline it. That seems like it's important. Their population declines. That word declines is important, right? That's telling us how it grows or decays by 1/4 each year. Well, if I write 1/4, right, it's a fraction. Does that agree with the decline? Yes, it does, because our multiplier is between 0 and 1. And that 25,000, right, that is our starting amount. So this equation, y equals 25,000, and then 1/4 to the power of x. Right, starting amount, multiplier, and to the power of x. So to the nearest whole number, how many polar bears will be left after 5 years? It's 25,000, 1/4, into the power of 5. All right, so when we do this in the calculator, we're going to have to do a couple things first. And that first part is going to be, let's take care of that 1/4. So I'm going to take 1 divided by 4. I'm going to press enter. Give it to me in a decimal as 0.25, right, which that makes sense. I'm going to take it to the power of 5. So to take it to the power of 5, we're going to look for this caret button. It's like an upwards arrow. It is diagonal from the number 7 on this calculator. So if I press that, it's taking my previous answer, which was 0.25, and it's saying, okay, to what power do we want to take it to? We want to take it to the power of 5. So when I do that, we get a really small number. Now I can go ahead and write that down, but right, that's a lot to kind of keep track of and then to retype in our calculator. So what I'm actually going to do is that is what 1/4 to the power of 5 worked out to be, and we just need to multiply it by 25,000. So I'm just going to press times, and it again shows the answer, so the previous amount we had, and I'm going to multiply it by 25,000. Get 24.41. Which is an extremely small amount. Right, so about 24 polar bears left. Right now, obviously not that realistic, but still we can see the power of these percents and how quickly things can either decrease, or if we did the opposite and increase, how quickly they can go. All right, so these are kind of problems that we have seen, right? If we're given a starting amount and just simply a multiplier. Now, again, we're going to skip number 6. That's something you can do in class. We're going to flip this page over. We have another set of exponential equations that we need to look at. So with these, you're going to see that you're going to be given a rate or a percent rather than a multiplier. So when we have this, our equation is very similar to what we saw on the other side, where we have A, which is our starting amount. But now for what used to be the multiplier, we're going to have 1, I'll explain what that 1 means in a sec, plus R to the power of T. Well, R is percent growth, and T is just time. Now, we're going to be given a percent. So one thing that's really important with percentages is to really understand what that means, right? A percentage is out of 100 typically. So what we want when we're using percentages in these equations is we need to convert them into decimals. When I say percent growth, we're going to say percent growth, but need to convert to decimal. We'll explain how to do that here in just a little bit. This 1, I said I would talk about what that means. This really stands for the 100%. So when we say something is growing by a percentage, let's say 5%, that means we are keeping the original 100% of where we started, and and we're just adding on an additional 5%. Okay, so this 1 is always, it's kind of how we get to that growth, or here in a second, get to the decay. Okay, it stands for the 100% of what we're either keeping and then adding on to, or the 100% that we're keeping and then taking away from with exponential decay. So we always get that question, what is that 1 for? I know it's something that's new, it's a little tricky, but as we start to work with these problems, they start to make a little more sense. So not too different from the equation we wrote on the last page. It's just we don't have a multiplier, right? We have a percentage. For exponential decay, really same thing, except it's 1 minus that percentage to the power of t, right? So a still is the starting amount, r is still your percent growth or decay, converted to a decimal, and t is still your time. Okay, none of that has changed. I don't need to relabel it. It's just we want to subtract that percentage away from 100, right? So think about this. If we again have 5% decay, that means we originally have 100%. So if we're taking away 5%, right, we really want to keep 95% of what we started with. And so that's how we get that amount. Okay, so it takes a little more conceptualizing as to, okay, what do these percents do and how can we represent that in our equation? All right, so based on the multiplier, we can decide whether or not something has exponential growth or decay. And we've talked about this already, right? When we did graphs, we talked about something going uphill, and it goes uphill whenever that multiplier was a number bigger than 1. And it was going downhill whenever our multiplier was a number smaller than 1, but we want to be careful there and say between 0 and 1, because we won't ever have a multiplier that is negative. So here, if we got 14 times 2 to the power of x, this multiplier is 2, so that's going to be growth, because it's bigger than 1. 0.97 is smaller than 1, so that's going to be decay. Right? So we're really only focused on what is the value that is to the power of x. So for C, smaller than 1, that is decay. And 1.089, barely bigger than 1, but still bigger than 1. So that is growth. Now, we want to write all rates as a decimal. That's something I talked about at the top, that if we have a percentage, we need to convert it to a decimal. So how we can do that is if we just take the percentage and divide it by 100. Now there's much quicker ways to do this. You can move the decimal 2 places. I think this is really the easiest and allows us to use our calculator, but some of you probably have quicker ways, and that's okay. So the percentage here is 4. So if I take 4 and divide it by 100, it'll tell me exactly what the decimal is that I need to use. So it would be 0.04. And like I said, if we had the decimal, right, it'd be after the 4. That's what. And then if I move it left 2, get to here, and we fill in the gap with a 0, so 0.04. Right, 5.75, let's divide it by 100. And we get 0.0575. Again, you could have just moved the decimal. And our last one, if I take the percentage of 12 and divide it by 100, I get 0.12. Okay, so let's go ahead and try one of these problems out. And we're going to write down a bunch of stuff to help us get to that equation and then help us go ahead and use the equation to make a prediction. So the number of students enrolled at a college is 15,000. I still want to use that method of finding the important words, right? Taking the math away from the problem. So identifying that 15,000 is really important. The word grows is also important, and the fact that we have percentage tells us that we're in exponential growth or decay. Now, since it said grows, obviously we're going to use our growth equation. I also identified the year just to make sure that all my times are being matched up correctly. So exponential growth or decay, this is growth because of the word growth, right? We see that. What is the initial amount? Well, it started with 15,000 students. And their rate is 4%. But remember, we don't want to use 4% in the equation. We need to take 4 divided by 100, and we get 0.04. That's the percent or the rate that we want to use in our equation. That has been converted to a decimal. So our full equation is y equals 15,000, 1 plus 0.04 into the power of t, which is time, or we can still use x, it doesn't really matter. But we don't have a value of that time yet. Now, one thing that's really helpful here, right, is if we think about PEMDAS or order of operations, it says to simplify your parentheses. We can still do that, right? 1 plus 0.04, well, that's just 1.04. That makes this a little bit easier to work with in the calculator. So we're not having to type everything in, and we can just move a little bit quicker through these problems. So I'm going to always encourage you to go ahead and simplify that percent that is in the parentheses. Right, so we're going to figure out how many students will be enrolled after 25 years. Well, that is our time, right? Years is what it was given in. So we're going to take our simplified equation, 15,000, 1.04, and take it to the power of 25. Again, when we do this in the calculator, we got to do the exponent first. So I take 1.04 to the power of 25. We get a really long number. We can go ahead and write that down. Again, that's a lot to write down and keep track of and then have to retype in the calculator. So what I'm going to do is actually keep this amount by pressing times. So it just says answer. I'm going to multiply it by 15,000. And I get 3,998.7.54. Now we want to stop here and be like, okay, does this value make sense? Well, it's growing. So let's first make sure it's bigger than where we started, right? 15,000 to 39,000. Yes, right? It definitely did grow. Now, it seems like a lot, but when we think about 4% every year for 25 straight years, the amount of which is growing is increasing every single year. So even though it seems like a lot, we're at least growing, and it seems to go ahead and work. So when we do this, we just want to give an estimate. So we have 0.54, obviously, and there's no such thing as 0.54 of a student. Let's go ahead and round that up and say we would estimate that there are 39,988 students enrolled after 25 years, which is a lot, right? That's a lot of growth over that amount of time. All right, let's just go ahead and set up one more, and then we'll call it done for this lesson. So this is our next page, looking at number 9. Okay, same idea. Let's go ahead and identify some of the important words and then work through each question to help us come up with the equation and then make predictions. So the population of the city is 45,000. That's important. That's our starting amount. It decreases 2% each year. Again, right, that amount, 2% is important. The word decreases tells us that we want to use exponential decay, not exponential growth. And then the years, we want to, again, just make sure that all our times are matching up. Everything's in the years, so that part is taken care of. So this is exponential decay because it decreases. Our initial amount is 45,000. Our growth or decay rate is 2%, but converted to a decimal is 0.02. Right after I divide it by 100. So our equation, and this is where I got to be very careful, is 45,000, 1 minus 0.02 to the power of t, right? That minus is really important here. Because it's decay, we need this multiplier to be less than 1, right? If we would have went ahead and did 1 plus 0.02, it'd be growth, and we get a completely different value than what we should get. So just like before, I want to go ahead and simplify the inside of this equation. It's a little bit harder, right? Adding onto 1 is easy. Subtracting from 1, a little bit more to think about. So 1 minus 0.02 is 0.98. Now again, I'm going to stop and just say, does that make sense? Well, yes, right? If that multiplier is less than 1, that tells us that this is exponential decay, and that's what we were looking for this whole time. So everything seems to check out so far. And what we need to do is take 45,000, 0.98, and we're seeing how long, or what would it be in 15 years, so to the power of 15. I'm going to take that 0.98 to the power of 15. It's going to give me a weird number, right? 0.738569103. I don't want to write that down. It's a lot to keep track of, so I'm just going to go ahead and press times 45,000. It tells me, and we get 3,000 or 33,235.6. Now again, does this make sense? Are we decreasing? Yes, we're decreasing, right? That'd be the one thing to look for first. And does the amount seem right? Well, again, it's a big jump, but after 15 years, right, 2% starts to add up. So this seems like a logical amount of what we should be getting. But again, we have this 0.6, so let's go and round that up. This is just an estimate. So we're going to say after 15 years, the population will be about 33,236 people. Okay, so just at least putting that problem in some context. All right, well, that is it for Unit 3. There's lots to do in this exponential lesson, so continue to practice with it. Make sure that you do complete your video check-in, and then we will see you in class next time.